Modern engineers developing high-entropy alloys and solid-state batteries are hitting a processing wall. Predicting how a new material deforms traditionally depends on density functional theory, a process requiring the solution of many-body Schrödinger equations for every atom in the system. These calculations scale at a cubic rate. As the simulation size grows, the computational cost becomes unsustainable for high-throughput screening. While accurate at the atomic scale, this overhead makes it impossible to simulate the large-scale supercells needed to predict bulk mechanical properties. A new metric called topological friction suggests a different approach. Macroscopic ductility is governed by the discrete geometry of the atomic bond network. By translating crystalline supercells into pure graph-theoretic abstractions, researchers can evaluate material behavior without invoking quantum mechanics or thermodynamics. This abstraction allows for the algorithmic evaluation of a lattice in a fraction of the time required by standard simulations. Treating ductility as a network routing problem provides a scalable screening mechanism for materials discovery. The process begins by mapping a continuous 3D atomic lattice into a coordinate framework of floating nodes. In this graph, individual atoms are nodes, and nearest neighbor chemical bonds are established as connecting edges based on a strict distance threshold. When a crystal undergoes plastic deformation, a dislocation moves through the lattice. This requires breaking an existing bond and immediately forming a new one. This physical bond breaking is mathematically equivalent to deleting an edge within the graph network. Once the lattice is mapped as a graph, evaluating a material's plasticity becomes a purely geometric calculation. Consider a single bond deep within a fully coordinated cluster of the atomic network. To simulate a moving dislocation core, we virtually sever this specific connection, completely removing the edge from the graph. A breadth-first search algorithm then begins scanning outward from the severed nodes, searching for an alternative connection. The algorithm identifies the shortest possible alternative path that still links the two separated points. The length of this bypass is the SE metric, or topological friction. This value is identical to the length of the shortest cycle that contained the original bond. A higher SE value indicates that the dislocation requires a more complex, long-range atomic rearrangement to bypass the defect. Topological friction quantifies the local structural effort required to maintain connectivity when a bond is broken. We can see this in face-centered cubic metals like copper and gold. Computational analysis of FCC networks reveals a 100% SE equals 3 distribution. Because of the dense packing, every single bond in the lattice participates in an immediate 3-step cycle. This local redundancy allows for seamless atomic handoffs. As a dislocation glides, an immediately adjacent atom is always available to accept the new bond. The high ductility of FCC metals is preconditioned by this absolute topological redundancy. Body-centered cubic structures, like iron and tungsten, behave differently. They lack the close-packed planes found in FCC metals. In the topological evaluation of BCC lattices, the SE equals 3 fraction is precisely 0. This 0% result is a direct consequence of the bipartite frictional lower bound. A bipartite graph is one where nodes can be divided into 2 sets, with no connections allowed within a single set. Because connections only exist between the 2 sets, bipartite networks mathematically prohibit odd-length cycles like triangles. With triangles impossible, the topological friction for any bond must be an SE of 4 or higher. This constraint forces the dislocation core to coordinate movements over a much larger lattice spacing. The higher lattice friction and the brittleness of BCC metals is a direct consequence of this graph-theoretic constraint. Simple hexagonal lattices show how this metric manages direction-dependent physics. The analysis shows a split. SE equals 3 routes are abundant within basal planes, but the bridges between layers are restricted to SE equals 4. This numerical split maps to the real-world physical slip anisotropy found in metals like titanium. The limit of this scale is found in tetrahedrally coordinated structures like diamond and silicon. The diamond lattice yields a monolithic topological profile of 100% SE equals 6. There are no triangles or quadrilaterals. Bypassing any defect requires motion across a full 6-membered ring. This SE equals 6 signature is a predictor of absolute topological rigidity and mechanical brittleness. This topological constraint appears in domains entirely separate from metallurgy. There is a structural equivalence between the diamond lattice and the Heawood graph. The six-membered chair ring of the diamond crystal forms a loop with no internal cross-connections. The abstract Heawood graph shares this same bipartite node structure and hexagonal layout. Both structures belong to the same Girth-6 topological class. In error-correcting silicon hardware, Girth-6 topology is engineered to prevent short-cycle trapping sets during data decoding. The lack of short bypasses creates signal traps in data hardware, just as it creates defect pinning in covalent crystals. A lack of local redundancy increases system fragility, whether the network is routing a bit or a physical dislocation. This metric also provides a lens for evaluating biological neural connectomes. Mathing the nervous systems like C. elegans reveals massive redundancy, with over 90% S=3 fractions. Biological brains mathematically cluster with ductile metals like gold, rather than brittle ones like diamond. This topology allows a nervous system to locally bypass noisy or damaged synaptic connections. S=3 dominance represents a shared structural signature for systems requiring fault-tolerant routing. Whether a network is composed of metallic bonds or biological synapses, the availability of immediate topological bypasses is a prerequisite for stability under local stress.